Okay. Let's just assume.
Oh, there we go. Creepy.
All right. Hi, I'm Sam. I'm the maintainer of the recursion schemes library, and I do many other things. You can follow me on Twitter. My username is Haskell_cat. I also have a YouTube channel I use to stream some Haskell pairing sessions. But today's topic is recursion schemes. I don't have a lot of time, so let's focus on that topic. I will share my screen so you can see the documentation for the recursion schemes package. Is the font big enough? I guess I can make it a bit bigger just in case. What are recursion schemes? Well, we're looking at the documentation, and so the README should answer that question. Recursion schemes is something that, as a Haskell programmer, you should already be familiar with, just not under that name, because you probably all know about fold R, right? And what is fold R? It's a function which abstracts over a very common pattern, right? When you write a recursive function, such as sum or product, the very typical way in which you write this function is you pattern match over all of the constructors on the input. So list has a nil constructor and a const constructor, pattern match on it, you put something on the right-hand side. It turns out that for many of the functions we write, this right-hand side has a particular pattern. For sum and product, in both cases, the right-hand side for the const case is we are making a recursive call on the tail, and then we're combining the result with the value for the head. In the case of sum, we're combining it with plus. In the case of product, we're combining it with times. And so with fold R, it allows us to write these implementations in a much more succinct way. Instead of writing the code which pattern matches on the two constructors and makes the recursive call, we can just say, we can just write down the parts which differ. That for sum, we're combining with plus, and we're starting at 0 in the nil case. And for product, we're starting with 1, and we're combining with times. Right? So that is a recursion scheme. It does not come from the recursion schemes library. It comes from the prelude. But it is a recursion scheme in the sense that it is a function which captures a recursion pattern, the fact that we are recurring on the tail. And there are other such functions which the recursion schemes library provides. So let's look at other examples of recursion scheme functions, unless there's a question. I want to pause often and ask that. Apparently not. Let's look at other examples, because fold R only works for lists. If it happens that you're using a list, fold R is great. But let's say you're working on a tree. What are you going to do then? So here are, again, 2 example functions that have a tree as an input. And so what they're going to do, they're going to pattern match on all the constructors. It just so happens that the tree has only 1 constructor. Let's look at its definition. It has 1 constructor node, which has an element, and a list of children, which are themselves trees. And so the way in which the recursion terminates is that eventually you hit a node which has a value, and it has an empty list of children. So that's how leaves are represented. There's not a separate constructor for leaves. So if we want to calculate the depth of the tree, which is the length of the maximal path, the length of the longest path from the root to a leaf, we can calculate it like that by recurring on the subtrees, taking the maximum of their depths and then adding 1 to it for the current node. And if we want instead the size of the tree, that is the number of nodes, then instead of the maximum, we're using sum. But in both cases, we recur on the subtrees. Here, you don't see the recursion because I intentionally put a bug in the code so that I can then later in the documentation say, did you spot the code, but the bug? But I'm trying to go relatively quickly, so I'm not doing this pedagogical trick on you today. I'm telling you the solution already. But anyway, the idea is that once again, we can use a function like fold_r, which in fact is provided by the containers package in the elimination section. We have a fold_tree function that behaves the same as fold_r in the sense that you provide it with the thing that differs, and fold_r or fold_tree will do the thing that is the same in all of those functions, namely recurring on the children. And so here you give it a function for how to combine the label, the value for, it's called the label, like the value for the current node, and what to do with not a list of children, but a list of b's, right? B is the output value, a list of the results that have been recursively computed for each of the children. So you don't have to make the recursive call in order to get to transform the list of trees to a list of b's. It is fold_tree which does that for you. So in the recursion scheme, it doesn't look quite like that. It's completely equivalent, but we have this function called kata for katamorphism, and like all of the recursion schemes have some impossible to remember Greek names. So please don't waste some brain space trying to remember them during the talk. You can look them up later. I think it's much more important to focus on the ideas than on the names. So it happens to be called kata. And it is general enough that it works for both lists and trees. Okay, so it's a generalization of fold_r and fold_tree. And how does it do that? If we look at the code for the type for so I want fold_r. If we look at the type for fold_r, I would like a specialized version for lists. I'll just write it down here. List. I can compare with type of fold_tree, which is a very similar function, but for trees instead of lists. I'm claiming that kata is somehow general enough that it can go from T to B, where T can be either instantiated to a list or a tree or something else. Any questions so far? I guess not. So how are we going to do this? And it's going to be a challenge because fold_r already differs from fold_tree quite a lot. It's not just that in one case it's a list of A, and in the other case it's a tree of A. Like, this is easy to generalize. We can use a type variable T and say we can either instantiate T to list or to tree A. But here, fold_r has 2 arguments, whereas fold_tree has 1. And so how do we unify that? Well, the first thing to do is to notice that both of those arguments produce a B. So we could start to group together those 2 functions by making this one into a function from unit to B. And then if it is a function from, okay, this could also be like from a pair, A comma B, like this is still equivalent. I haven't changed anything, but I'm slowly massaging the type signature so that it gets into a form that can be unified with the type vector here. So this one I'll also make it into a pair. Okay, so they're getting closer and closer, but there's still 2 arguments for fold_r and 1 argument for fold_tree. And the last trick is to use either A comma B or unit to B, so that if it's a left, then I'll apply the function that was from A comma B to B, and if it's a right, I'll apply the function from unit to B. So now it's completely equivalent to what I had before, but now it's much clearer how I can unify the 2. So it's going to be from some input I to B to T to B. where I would either be either a comma b or to be a comma list of b. Because of course I can't implement kata because it's like way too generic. Right? I'm claiming that given a function from I to b, I can implement a function from t to b, but like there's nothing which ties together I and t. And so the last trick is
One question. Does the
yes,
T
question?
kata does the T in kata stand for any functor?
Not a functor, no. If it was a functor, it would be something like P of A. But here, T stands for either list of A or tree A. So it stands for a recursive structure, not a functor.
Okay.
Like it could be, for example, nat, z or successor of nat. This one is not a functor because there's no type parameter, but it is a recursive structure. So T could be, like, I could have fold nat from either unit to represent z or b, because the recursive position where the nat is, we will be receiving the value that has been called, the value of the recursive call at the position. If it's a b, not a nat, to a b, I'll just transform a nat to a b. That would be the instantiation of kata for nat. So I need to show that there's a link between I and t. And the way I'm going to do this is using one last simplification. I will be messaging those types a bit further, and that's going to be by creating new types which are functors. So here I'm going to create a type called natf, which means it's going to be very similar. I'll add an f just because I'm not allowed to have the same constructor name twice. But instead of taking a nat here, it's going to take an r. And same thing for list f, or cons with an r instead of a recursive list, and tree f, a node f with a list of r's instead of a list of trees. Okay, so those tree functors, they are functors this time because I've replaced all of the recursive occurrences of the type with a type parameter. Those type constructors, those type constructors are functors, and they are isomorphic to the thing that I put on the left of the functions. That will make things a lot more readable. So here, either unit B is isomorphic to nat fb, and either a comma b unit is isomorphic to list tfab, and a comma list of b is isomorphic to tree fab. So now that I've done that, well, I can't use I here. I need to use IB, and the thing that is here is like TF. Right here I have nat f, list f, tree f, and now it's much clearer how to specify the link between T and TF. Is that there needs to be a project function that is able to expand a T into a TF of T. So, for example, nat is isomorphic to nat f of nat. If I instantiate R to nat, then I get the same recursive type that I had originally. Anyway, so that's the type of kata. Go back to the documentation. Here's what it looks like to use kata to implement depth or size. So what is the part which differs? In this case, it doesn't really make the implementation more succinct, but it's more to explain how kata works than to demonstrate where it shines. Where I implement it, I call kata on a function of type 3FAB2B. So what is B in this case? It's int. So 3FA int to int. And it's calculating the depth. How? Well, the node F has the A that we're not looking at, and not a list of subtrees, but a list of the results, right? Because kata has done the recursive call for us. And so now we can take the maximum of the subdepths. And unlike here, where there was an intentional bug and it didn't type check, here it does type check. So I can write 1 plus maximum subdepth, and similarly for the size. Any questions so far?
I guess I had maybe just a question about intuition. Like, is there any, am I right in thinking that there's not really any connection between foldable and kata? Because tree has like a foldable instance, so you could have like fold R, the more general fold R that you had before you specialized it to list, would work for tree, but that would be different from fold tree.
Indeed, they would be very different. Fold R, when it is generalized to work on an arbitrary foldable as opposed to just on lists, the way in which it accumulates the data is by going through all of the elements, in the case the A's, but it goes over them in a different order than if you were using kata. So if I go back to the definition of a list, or counts a list of A, right? So with fold R specialized to list and with kata, the direction in which the information flows is always from the leaves up to the root, right? We're making recursive calls on all of the children, and then we're combining the result with the value for the current node, and that will be used by the parent node and so on all the way to the root. And so for fold R, well, we're using fold R, not fold L, so the information flows from right to left. We are making a recursive call on the tail, and so that's the same direction. Where it differs, so fold R and kata are the same for lists, but for trees, so tree is a node of a label and a list of trees. So for kata, we make a recursive call on all of the trees, and so the information starts at the leaves, and then it is gathered one level up, and then all of the results one level up are gathered one level up again, until we get to the root. The information flows from the leaves all the way up. Whereas fold R, it's not what it does. Instead, it kind of does an in-order traversal of the tree. Like it goes to the leftmost leaf, and then to the second leftmost leaf, and then the third leftmost leaf, all the way to the rightmost leaf. Well, not just leaf, but like node, leftmost node, and then all the way to the rightmost node. And that allows you to combine the data, all of the A's, using a binary function, just like fold R, something that takes an, let's put the type of fold R. Didn't I already have it? Yeah, here it is. But now I had specialized it to list. Now I want to specialize it to tree. But that's not the type of fold R anymore. I've massaged it too much. Okay, so let me copy it again. Okay, so if T is tree, right? So we still have a one special value here, but this time it does not correspond to the constructor nil. Right? It corresponds to what do we want to do if the tree is empty. And that's never going to happen because the only constructor we have is node, and it has at least one A. Okay. And then we have this binary function, which adds one A. It accumulates it to the sum that we have so far. Not the sum, but like the accumulated value. It could be the sum if A is an int, but in the case of size, for example, we could be accumulating to the value we have so far by adding one, or with product by multiplying, whatever. And it's a binary function, right? You're only adding one element, one A at a time to what you have so far. Whereas with kata, for the tree, it's a unary function, right? Well, tree f stands. It's actually still a binary function, but it's a different binary function, right? It was a result of massaging fold tree, which takes a binary function. It's a very different binary function, right? I'm not combining an A with a B. I'm combining an A with a list of Bs, right? I'm not adding one A to the value I have accumulated so far as I was traversing all of the nodes from left to right, but rather I'm saying how to combine the element from the current node with all of the values for the children. The data goes up the tree and not from left to right. I hope that was clear.
Yeah, I think that helps.
Okay, so I accidentally went over this possible item on the menu because my intention was to go over the README for recursion schemes and then ask the audience if there are other topics that you would like me to cover, because there's a lot of cool things about recursion scheme, and the scheduled amount of time we have today is not long enough for me to explain everything. So I want to focus on the things people care about.
I'd like to know the big picture benefits. Like when I went and looked at the original fucking thing, he said that you can get optimal. You can get fusion, you can get optical traversals, all sorts of great benefits. And like, I haven't gotten far enough in. Are those things true? Is it like you can just almost always get a better, faster thing with a recursion scheme?
I would not say so, no. The recursion scheme library that I maintain, at least, is not particularly focused on performance. There are many other competing libraries, perhaps some of them are. But there is one big relation with performance that I was prepared to talk about. Let me just add a bunch of white space at the bottom so that the screen would stop moving around. Okay, so this one, performance via equational reasoning. So in the original paper, which introduced recursion schemes, which is functional programming with lenses, bananas, and enveloped and barbed wire, which is very hard to read because they use a notation which like nobody else uses. And the reason they use this notation is because they want to encourage you to write your programs in the same way mathematicians solve equations. Right? When you solve for x, you start with a big complicated equation, and then you're like massaging the equation to like isolate the x, and like you change an addition for a subtraction on the other side of the equal sign, and then you divide everything by the coefficient, or you do some bigger changes. If there are like x squared, you're trying to like factor out the equation into a form that is a bit easier to manipulate. And so in that paper, they recommend doing something similar, but for programs, where you begin with something that is very close to the specification of what you want the program to do. And well, you write it in a way that is executable, so it's already a program, but it's often not a very efficient program. And they are showing you that the same kind of symbolic manipulation of equations that you can perform in order to isolate the x or to simplify a mathematical expression into factors or something. You can use it to transform your program into an equivalent program that runs faster. And they make this a bit easier by making the programs a lot shorter. And that's why they introduced this notation called bananas, lenses, envelope, and barbed wire. Let me show you what it looks like. Like this parenthesis pipe is supposed to be a lens. And this square bracket parenthesis is supposed to be, I guess, a concave lens. One of them is an envelope, and one of them is a barbed wire. I think this one, double square brackets, are envelopes, and let's see, barbed wires eventually. Yeah, they have like daggers. Like they have lots of very succinct symbols to represent things like fmap and bimap and kata and a whole bunch of other operations that we typically write out using ASCII characters and therefore take more space on the screen. And so doing the kind of rewriting like in several steps that they propose would involve writing several versions of the same program, which I guess we do. We just don't do it like on a page on a sheet of paper. We just edit the code in our editor, and each subsequent notification is a different version of the programs. I think it was kind of an early version of equational reasoning, where you know that you can transform your Haskell program into an equivalent Haskell program by replacing one expression with another that you know is equivalent, but it's equivalent only in the sense that it computes the same result, not in that it does it in the same way, and it can do it faster. And so one example of that is switching from para to Zigo. So far, I've only introduced kata, so I guess I'll have to introduce para and Zigo before I can explain how to use equational reasoning to rewrite from one to the other. So let me do that. Actually, let me do that here. So I have some slides. I won't be using them. So let's look at it in the. Oh yeah, let's just look at it in the documentation for recursion schemes. So I look at folds. I look at para. So para is very similar to kata in that you also give it a function from something to, I called it B, now I'm calling it A, to A, and that allows me to give a function from T to A. So that thing in the case of kata, like it's called an F algebra, that again, the complicated names don't matter, but the shape is slightly different. Oh, there's this extra base that makes things look more complicated than they are. But like, think of this as if this is list, then base T is list F. So list F of A arrow A in the case of kata, list F of A arrow A. And here for para, it's list F of a pair of a list and an A. Arrow A. So what is this extra list A that I get? It's the original list. So remember, we are, like, kata is automatically calling recursively. It's calling your function recursively on the tail of the list. Or in the case of a tree, it's calling your function recursively on all of the children. And it's only giving you the result. And then you have to combine only those results into the result for your node. And sometimes that's too restrictive. And so para is a variant where, in addition to giving you the result, they also give you the original tail of the list or the original list of children, so that if you have other things that you want to calculate on it, you can do it by looking at that original list or on the original subtree. And Zigo is very similar. It's one of those I don't yet have a great documentation for in the official one, but maybe I can show you the in-progress documentation on gelineau.com/files. Codec recursion schemes. Look at Para and Zigo. Is this a good example? Zigo. Okay, so Zigo is a variant of Para where instead of receiving here the list, the original list for like the original rest of the list or the original list of subtrees, you get a B where this B is computed by another F algebra. And the reason Zigo exists is specifically in order to improve the performance over calling kata on that list. So let's look at a concrete example. If I want to implement this function, nub end, which is a function which, as you can see from an example, it's the same as nub, which is the function in base which eliminates all but the first occurrence of a value. So here there's a whole bunch of 2s. There's some before the tree and there's some after the tree. And so we keep the one that is before the tree. So here nub end is a function I would be defining that keeps the one after the after the tree. So we're keeping the last tree and the last 2 and the last 1 and the last 4, as opposed to in nub we were keeping the first 1, the first 2, the first 3, and the first 4. So if I want to implement this function, I could implement it in a naive way, or I could implement it in a more performant way. So the naive way would be to do so with Para. So let's do it with Para first. And with Para, you would get a list f int of the rest of the list. List of int. No, not this one. It's in Go. So Go here, we would be receiving the rest of the list and the already compacted list, right? The result of calling nub and on the tail. So in our example we have here, if I'm looking at the 1, the tail is everything but the 1. That's the original rest of the list. But I can recur. I can call nub end on the rest of the list, and then I will keep the last occurrence of the 4, the last occurrence of the 1, the last occurrence of the 2, and the only occurrence of the 3. Okay, so that's the recursive result of this second list result. Okay, I want to go from there to realize that since the 1 is already in that result, I don't need to add it again. Okay, and one naive way to do that in the const case, so not scene, but like the original and the compacted version, I could ask if the element I'm trying to add is already an element of the original list, then I just return the compacted one. And if the element is not in the compacted one, then I add it to the compacted one. Right? If this was a 9, then I would want to add a 9 2, 3, 9, 3, 2, 1, 4. Right? So that's what this logic is doing. But this is very inefficient. Well, for a few reasons. One of them is that I'm going through the list. It's a linear algorithm. What if we had a set instead? So like set the member of set the from list. But that's still inefficient because, well, I still need linear time in order to construct the set from the list. Okay, but I'm doing equational reasoning, right? I'm changing the program to something that has the same behavior, but it's doing it in a slightly different way, and that will allow me to slowly get to a program that is more efficient. But I'm not doing it with the squiggles and the envelopes, but you could. So the next step from that is to realize that this set, I can construct it iteratively using another kata. I can say kata of set.insert x into the list so far. I'm starting go prime of the original list, go prime, since it's kata, it's from list f, it of, this time there's not a pair of the original list and the recursive result, it's just a recursive result, so that's a set of ints to a set of ints, go prime, in the nil case, it's the empty set, and in the cons case, I get both the value that I want to add to the set and the set so far. So I can just do set.insert x into the set so far. So this is still as inefficient as before. I've just rewritten it using kata, because now that I've finally done that, since I have a para of something that uses kata, I can now rewrite it into a Zigo of go prime, and then instead of calculating kata on the original value, here I will receive the result, the set int. So I will ask on the set so far, if x is a member, so far. And now that will finally be efficient, because the way in which Zigo is implemented is not by calling kata on the entirety of the rest of the list each time, like that would be quadratic overall, but instead by constructing both the result of nub and constructing the set. As we go from right to left, right, we start with an empty set and an empty list, and I'm adding more and more entries to the set, and I'm also, according to this logic, deciding whether to add more and more items to the list. And so that is finally a linear algorithm instead of a quadratic algorithm.
So is the secret to like know how these all relate to each other and then you can compose them correctly? Or like
the secret for the performance is to know what are the equational reasoning rules that you're allowed to use, and to write your code in such a way that they can trigger. Right? So I intentionally introduced a kata so that I could eliminate it by switching from a para to a Zigo.
Okay, cool.
But you mentioned a bunch of other performance-related things, such as fusion. I guess there's another similar rewrite. It's not a rewrite rule because it doesn't fire automatically by GHC. It's something that you have to notice and do yourself, which is there's two different kinds of recursion schemes. There are some that create data structure, like from a seed, like let's say nats. This one is easier to implement without recursion schemes. It's just the numbers 1, 2, 3, and so on. But we can also implement it using the ANA recursion scheme, where we start from a seed, start from the seed 1, and we give it the function go from int to list f int and another seed. So I produce a cons of n, and I produce a bigger seed n plus 1, and then Anna will take care of taking this seed and using it to produce a bigger and a bigger and a bigger list. So that's Anna is constructing a bigger and bigger list, and kata would then be pattern matching on this cons f constructor in order to eliminate the list down to a value. So if you wanted to say take the sum of nats, which would just be infinite, but let's say we have a function that makes sense for an infinite list, like take 10. If you implemented take 10 in terms of kata, if you call take 10 of nats, then
questions.
You have more questions?
Yeah, one of the questions was when you talked about how you have to notice these and they can't fire as GHC rules. Is there a reason that they can't fire as GHC rules? That was asked by Makaram.
No, there's not a good reason. We just haven't implemented it yet for recursion schemes, and it might be the case that competing libraries do.
Fair enough. Yeah. The second question was, is there introductory material on reasoning with these primitives other than the Bananas paper?
It didn't really catch on. So, and not that I'm aware of. The introduction material on recursion scheme that I tend to see on the internet are more about like listing the basic recursion schemes like kata and ana and hilo and para and zigo and histo, and just explaining like, okay, those are crazy Greek words, but like what is the specific pattern that they encode, and show you that, yeah, indeed, it is a pattern that occurs over and over. Maybe it's worth giving it a name.
And I had a question, which is your in-progress documentation available where like I could read it and perhaps help out?
So the in-progress documentation is here. I'll paste it in the chat. So this documentation came before the current documentation, and like I think it would really clash to just have this first part, which is just like nice, and all of the examples are related to each other, and it's written in a way that is pedagogically sound, and then after what's this one? After histo, all of the rest is like a bunch of random examples that don't relate to each other and are not as pedagogically sound. But I guess it would be better than the current state of not having anything for most of them. So I guess a PR to move in some of that documentation could help.
Could be tolerable. Well, we have about 10 minutes in the first hour. I guess I figured I was going to make space for people to ask questions. Although I'm happy to hear longer, but I don't know what other people's time constraints are.
I tried to go faster in order to fit the time, and I think that I both failed at making things comprehensible and at fitting the time. Should have focused on a much smaller subset of what I wanted to present.
I like the fact that it leads into the equational reasoning part. That's the part I really like. Makaram's just asked about bidirectional information flow.
Oh, good. That's one we can do very quickly. So I said that the information flows from the leaves up to the root, but very often you want information to flow down from the root down to the leaves. For example, to implement the regular nub instead of nub end, you wouldn't look at the tail of the list in order to figure out if the element that you are wondering whether to insert or not has already been inserted. You want to look at the prefix, the elements from the root down to the end of the list that you've already looked at. And so you want the information to flow both ways. And there's a common trick to do that. Which document in kata A? Or is it that one? This one. The common trick is you return a function. So here I'm writing a pretty printing function from a tree to this ASCII stuff. And I'm not writing, even though overall I want a function from a tree to a string, I'm not using kata or kata A, same thing, with a helper function that goes from a tree f of string to a string, but rather a tree f of functions from int to string to a function to int to string. And so what will end up happening is that we are constructing a function from the leaves up to the root, but each of those functions, they expect an input and they can modify it and then pass that modified input to the function from their children, right? And so the overall effect is that after you construct this big function, the function you will have at the root is a function that can accept the original input that you want to start with at the root, and then it will get modified as it goes down through the leaves. So that's what I mean by bidirectional information flow. You both recur on the leaves, so you get the result of recurring on the leaves, so the information flows up, but also as you recur, you can recur with a value that you modify using the information you have seen as you went down from the root to the leaves.
Cool. Any other questions? I think at this point, people can feel free to unmute and talk if they want to for questions.
Do you want to stop the recording?
I can do that. Yep, I will stop the recording.